Okay, hello guys, Mr. Beyond here again. At this time we're going to discuss about how to grasp the information from a titration curve that looks like this, one of the sample here, yeah. So from the titration curve, what information can you gain is basically these two, yeah. You want to identify the analyte and titrant, you want to calculate their concentrations. That's basically what you can see from a very general looking curve, not a detailed one. Okay, so first you might want to revisit what is analyte and what is a titrant. Analyte is something that we analyze in a titration, yes. So if you remember, the one that you put in the Erlenmeyer is the analyte. It is the sample, or what we call the initial solution. Okay. Meanwhile, the titrant is the solution that you put in the burette and what you add into the analyte. So this one is in Erlenmeyer. In the bottom titrant, you usually put in the burette. Okay. So first, what we want to see from the curve is the initial pH. This initial pH belongs to the analyte, of course. And then you also want to see the equivalence point. So basically, from a very general looking curve that is not showing detailed values all around the curve, yeah, this is just showing the shape. What you can get is the approximate value of the initial pH and the equivalence point. Another example might be like this, yeah. So it's talking about the indicator. So for example, first you see the analyte is here. The initial pH is quite low, around 2 or 3. Equivalence point, to look at it, you have to find the flat part of the curve and find the middle point. You don't have to find the exact pH of the equivalence point, but you need to at least guess, or approximately guessing it, at what pH it is. Is it 7? Is it above 7? Or is it below 7? That's all. Okay. Because for the information number 1, that means it could be strong or weak, acid or base for each of them. Of course, if the analyte is an acid, then titrant is a base, and the other way around. Okay, so for the example on this one, okay, the initial pH is very low, around 2 or 3, but the equivalence point, as you see, is above 8, which is quite basic or alkaline. Therefore, the indicator should use phenolphthalein and so on. But the main point is the equivalence point is higher than 7. That means at equivalence point, the solution is not neutral but closer to basic. So that means what you add into the solution is a strong base. Meanwhile, the starting point here is a weak acid. Okay, so you cannot just judge the pH and then you this is very low, this must be strong acid. Not always. You must see the equivalence point. Okay, so basically, if the equivalence point, or I should say EP, if it's 7, means both are strong. Yeah, strong with strong. Okay, if it's below 7, then it involves, okay, strong acid and weak base. If it's above 7, then it involves strong base and weak acid. As you can see in another example like this, okay, the equivalence point was way below 7, so it must involve a strong acid, and the other side must be weak base. For this level, mostly you're not encountering weak and weak, but if you want to know between weak and weak, the equivalence point is also around 7, and the curve was not very clear. Equivalence point, yeah, it's very narrow, but you don't have to worry about that. Back to our example. So in this case, the equivalence point has already shown you that it is 7, right? So it's strong and strong. And of course, since the starting pH is above 7, very base, so this is a strong base. So we can say that the analyte, from the initial pH, we know that the analyte is strong base, and the titrant is also strong acid in this case, because the equivalence point is 7. Yeah, perfectly neutral. Now For information number 2, how to calculate the concentration of analyte and titrant. Well, you need two informations for this, yeah. Must be given in the questions. The volume of analyte is 20 milliliter, means the analyte uses 20 milliliter, and the mole ratio of analyte or titrant is 1:1, means it's equimolar. For example, it's like NaOH and HCl, they are 1:1, right? So if the volume of analyte is 20 milliliter, okay, you can use that to find the concentration of titrant. But first we need to find the concentration of analyte from the pH. Initial pH. If you want to be diligent, you may need to measure it, but we can take a guess. It's around 13. Yeah. If it's 13, means it's basic, and you have to calculate the OH minus. Remember, yeah, you have to convert pH into pOH. Therefore, the pOH is 14 minus pH. 14 minus 13 becomes 1. And using some logarithm magic, we know that the OH minus will become 0.1 molar. If you still have problem with this, let me know. Okay, this is the concentration of analyte. Therefore, we can use this value to find the concentration of titrant. You can use the formula, which I hate to use, V1M1, but you can simply say that they have the same mole, right? The mole ratio is 1:1, so the amount of mole 20 milliliter and 0.1 molar is the same as 50 milliliter here. It's already been bolded, right? Yeah, 50 milliliter of the titrant times what? So we know that mole is molarity equals to mole per volume. Therefore, the mole is M times V. This is the origin of those formulas. So mole of the analyte is the same as the mole of titrant. 0.1 molar of the analyte times 20 milliliter. You can use milliliter because both of them are milliliter. Molarity of the titrant times, in equivalence point, it is 50 milliliter. Therefore, you can get molarity of titrant is equal to, yeah, you can calculate yourself. Okay, just has to look. Yeah, that's the example for a strong and strong. It looks like this. Now for the weak and strong, you need the value of Ka or Kb. If not given in the questions, you may want to ask your teacher about it. Okay, I guess that's it for today. The general idea in how to read the titration curve. If you have more questions, feel free to ask me. See you in the next video. Bye bye.